Hello everyone, I am Dr. Jaikishan Oja, Assistant Professor of Physics from Government Degree College, Lakshatpet. Today it's the sixth lecture on statistical mechanics, and today we will see the last topic in this chapter, that is the application of Fermi-Dirac statistics. So previously we have seen one of the applications of Fermi-Dirac statistics, that is your electron gas. So there we had seen the definitions of the concept of Fermi energy, what is Fermi energy, and we got some equation for the Fermi energy. So today we will see the uh, next application, that is the application of Fermi-Dirac statistics to white dwarfs and neutron stars. So before going to what is white dwarf, what is neutron stars, yeah, we should have some idea regarding the birth of the star and the death of a star, and what are the different processes involved in the death of a star. Okay, what are the different process through which a star can die? So first we have to see the birth of a star. So we know in the interstellar space, yes. So interstellar space is nothing but it is the space available between the stars. Yes. So we know stars are millions, billions miles away from our Earth. So at such distance, we have huge dust is there. So in the dust, you will be having different types of gas molecules. So here, this dust particles and gases, they combine together, means they are compressed together to form a cloud. Okay. So what happens due to this compression means a number of dust particles and gases will be coming together, and the size of the cloud will go on increasing. Yes, so why this happens? This happens because of the gravitational pull. Okay, there is a gravitational force. Because of this gravitational force, these dust particles and these gases will be coming together, and because of this gravitational pull, compression will take place, and all these molecules, means gas molecules and dust particles, will come together to form a cloud. Okay. So what happens? We know whenever there is a compression, means if you are applying pressure or if compression is there, naturally the temperature increases. And again, whenever you have expansion, the gas will cool by because the pressure decreases. So here what is happening? Here all the gas molecules are coming together, dust particles are coming together. So you have a compression because of gravitational forces. So because of this compression, the temperature of the cloud goes on increasing, so it heats. So uh, yeah, this clouds cannot keep the heat with themselves, so it will go on radiating this heat energy to the surroundings. So because of this radiation or giving away the heat to the surroundings, the cloud further contracts, and because of this contraction, again the temperature of the cloud goes on increasing. So a time comes when the temperature of the cloud becomes about 10 to power of 7 kelvins. So at this high temperature, the hydrogen atoms present in the cloud will combine together to give helium atoms. Yes, so it is a fusion reaction. So something, it's a nuclear reaction. Yeah. So because of this fusion reaction, a large amount of energy will be released. Yes, and because of this energy, the star will be shining. So that's why we are able to see this cloud, the cloud becoming a star, and this star is illuminating for millions of years as long as the reaction is going on. So this explains the birth of a star. Yes, so we have to remember that this is not our space, not in the normal space or normal clouds. Why? Because we know the normal clouds are formed in the troposphere of our atmosphere. But what we are speaking here is nothing but the space, which is the space between the stars. So it is millions, billions years, sorry, millions miles away from the Earth. Yes, so there we have large amount of dust and gases. So all these gases and dust are combining together because of the gravitational force. So they form a cloud, and naturally, what happens? The size of the cloud goes on increasing, but due to the gravitational pull, the cloud will go on contracting, and due to the contraction or compression, what happens? Heat is generated, and this heat is radiated, and again due to the radiation of the heat, the temperature of the cloud, the cloud goes on contracting further, and due to this contraction, again the temperature of the cloud goes on increasing. And at the central core, what happens? If the temperature is exceeding 10 to the power of 7 kelvins, then we have the nuclear fusion reaction. Here the fusion of hydrogen atoms into helium atom takes place, and a large amount of energy is released. And because of this energy, the star illuminates, and we are able to see the stars, and these stars will have millions of years of life. So this is nothing but the birth of the star. So next we will see how the star dies. So again, we'll go to the next slide. So here what happens is, we were saying that the star is in existence because of the thermonuclear, sorry, even thermonuclear or fusion reactions. Yes. So now what happens when all the hydrogen atoms of the star are converted into helium atoms? Then uh, the core of the star starts contracting. So we know, I was saying, yeah, due to this contraction, the temperature of the core or the star again rises. So the star cannot keep the heat with itself. So naturally, what happens? The central core of the star will give away the heat to the outer layers. So due to this transmission of heat to the outer layers will start expanding, and they will become very big in size. Now, what is happening? The outer layers will now go on expanding. So I was saying, due to the expansion, the temperature will fall. So the temperature of the outer layers continues to fall due to expansion. So how long this process continues? So this process will continue till the temperature of the outer layer falls enough to make the star appear red. Then the star is called as red giant. Now, at this condition, a violent explosion occurs in the star. Means there is a explosion in the star, and this we know is known as nova or supernova explosion. So, as this explosion, what happens? The outer layers will naturally be thrown back into the interstellar space, leaving behind only the core of the star. This is known as death of the star. So again, depending upon the size of the core, the star may end up into one of the three dead bodies. So it can die as a white dwarf or neutron star or black hole. So here comes the concept of white dwarf. Yes. So we have to remember that white dwarf is nothing but it is one of the final moments of a dying star. So we will see under what conditions this happens. So when the original mass of the star is less than 1.4 times the solar mass, then the core of the star tends to die, leaving a white dwarf. So this was theoretically discovered by S. Chandrasekhar in 1930 and is known as Chandrasekhar limit. So many times we come across this term. What is Chandrasekhar limit? So you should be very clear that Chandrasekhar limit is nothing but it is regarding the white dwarf. So as the core keeps on emitting heat, and light for millions of years, its color changes from white to yellow, then to red, and finally it becomes black. So when the star becomes black, you cannot see the star. So the star now becomes invisible forever. That is known as your white dwarf. Yes. So we have to remember the condition that whenever the original mass of the star is less than 1.4 times the solar mass, then the star will die as a white dwarf. So what happens if the mass is greater than 1.4 times? Then we have some other condition or other process of the star dying. So, so in between that, we have something known as neutron star is there. Uh, so we have three. I was saying three processes are there. One is white dwarf, neutron star, and black hole. So if the mass of the central core of the star is greater than 1.4 times, and if it is less than 5 times the mass of sun, then the core of the star tends to finish up as neutron star. So in such a case, when the supernova explosion occurs, the core of the star is compressed and electrons and protons combine to form neutrons. Due to this reason, this is called as neutron star. So it is found to have a radius of about 10 kilometers. So we have to remember this condition. Why? Because again, we will be repeating this neutron star. Why? Because we have the application, a specific application of the Fermi-Dirac statistics to neutron stars also. There we can repeat this. So the condition we have to remember is whenever the mass is greater than 1.4 times and less than 5 times the mass of sun, that is solar mass, then the core of the star will end up as a neutron star. So when does this happens? This happens when the supernova explosion is taking place. Then, as I was saying, you have a compression, so the electrons and protons will combine together to give a neutron. So this is the second condition. Then we have one more concept, black hole. So again, it's a popular term. We come across this term a number of times. So we should have some idea regarding this. What is a black hole? Um, So if the mass is less than 5 times, it was Newton star. So now what happens if the mass is greater than 5 times? So when the original mass of the star is more than 5 times the mass of the sun, then on supernova explosion, the core continues suffering compression indefinitely due to recoil. Then it gives rise to a black hole. So the mass of the black hole is always greater than the mass of the sun, but its size is very small. Due to this fact, what happens? We are saying that its mass is very large, so the gravitational pull of the black hole will be naturally very strong. So due to this strong gravitational pull, the photon of the emitted radiation cannot escape the surface of the star. Again, if any proton is approaching the black hole, it is swallowed by it. Hence, we call it as black hole. Yes. So, what is happening? Why we call it as black hole? Why? Because it any photons cannot escape it, and again, if any photon is approaching it, it will be swallowed. Yeah, photons is nothing but again it's a radiation. So this black hole will take away all the things. Yes, actually, it's a core. It's the core of the star. That's why we call it as black hole. Then we go to the real application of this Fermi-Dirac statistics to white dwarf. Why? Because now we got the idea. Yeah, what is white dwarf? What is a neutron star? What is a black hole? So, what is the role of Fermi-Dirac statistics? How we can explain the Fermi-Dirac statistics uh, to the ending of star as a white dwarf? So, you ever Yeah, our question here is, what is preventing the white dwarf from the further gravitational collapse in the absence of radiation pressure? So the answer of this question is the quantum mechanical effect known as electron degeneracy pressure. Yeah. So now we have to explain what is this electron degeneracy pressure. Yes, we know that already electrons are fermions. We know that this fermions, they obey Fermi-Dirac distribution law, and they obey the Pauli's exclusion principle. What is Pauli's exclusion principle? According to Pauli's exclusion principle, no two electrons can have exactly the same energy state. So as we have seen in the previous topic, your Fermi energy, we say that the electrons will have the energies right from 0 to the Fermi energy. So it is given as E suffix x. So we call this as Fermi energy, and the corresponding level is known as Fermi level. So we need to remember that all the levels from 0 to the Fermi level will be occupied by the electrons, and the levels or states above the Fermi level will be vacant or empty. So in case of metals, already we have seen the equation for the Fermi energy, which is given as your EF is equal to, yeah, we have EF is equal to h square by 2m into 3 by 8 by n by v whole to power of 2 by 3, where we know EF is known as Fermi energy, h is Planck's constant, m is the uh, mass of the electrons, then n is the number of electrons or the fermions here, and v is the volume. So this is the equation of your Fermi energy, and we know n by v is nothing but it's the density of the electrons. Yes, the white dwarf is very dense. Why it's very dense? Why? Because you have a large number of particles in a small volume. Why? Because we were saying that the core goes on contracting. Yes. So since there is a compression and contraction of the core, but the number of particles will be conserved there, so the density will be very large. So since the density is very large, what happens? We have high energy. The high energy electrons will exert very large pressure. Okay. So this pressure is known as your degeneracy pressure, and this pressure is responsible for maintaining the white dwarf. So we have to remember that this electron degeneracy pressure prevents the total collapse of the dead star white dwarfs, and it gives some finite radius to it. So uh, yeah, we should know what is the, we are saying it's having some finite radius. Okay, so when the thermonuclear reactions come to a end, means it halts, then the nuclei cools down and get collapsed under the gravitational attraction. But we know the Pauli's exclusion principle prohibits more than one electron to occupy the same energy state. Therefore, the electrons cannot cool down to occupy the lowest energy states. As the star shrinks more and more, the density will naturally become very large, means NYV becomes very large. So as a result, the Fermi energy EF becomes larger and larger. So the electron degeneracy pressure increases more and more, and at a certain stage what happens, the electron degeneracy pressure balances the gravitational attraction. So this determines the size of white dwarf, means at which position, at which level you have the balance between the electron degeneracy pressure and gravitational attraction. At that level, the size will be the size of white dwarf. So this we can say that Fermi-Dirac statistics successfully explains the stable existence of white dwarf. Okay, so it is dying, but we are saying it is having some finite radius. So this is happening because of the Fermi-Dirac statistics. So as we were repeating a number of times, you cannot have all the electrons in the ground state. Means you'll be having the continuous distribution of electrons in different levels up to the Fermi level. Hence, the nuclei will not cool down and it will not uh, collapse that easy. So this is about the size of the white dwarf. So next, our other application is neutron stars. So already we have discussed the formation of neutron star. Once again, we can see this. So whenever the mass is greater than 1.4 times the mass of the sun, the gravitational pull will be more predominant than electron degeneracy pressure. So the white dwarf cannot be stable any long and it shrinks further and results in a neutron star. So whenever the mass of the star is greater than 1.4 times the solar mass and less than 5 times, then the Fermi energy reaches about 1.1 MeV, okay, million electron volts. So the average electron energy will be about zero point 0.8 MeV. So this energy will be sufficient for an electron to react with a proton to produce a neutron. Yes, we know this process. Electron, a combination of electron and proton will give a neutron. But we need sufficient energy for this reaction to happen. So this process continues until the star acquires a density of about 20 times the density of original white dwarf. Afterwards, there will be only neutrons in the star. Therefore, this is known as neutron star. We know that neutron is far less in size than an atom. Why? Because neutron is just a constituent of atom. In the atom, we know we have neutrons in the nuclei. So naturally, the size is very less when compared with an atom. So the neutron star will be quite dense. Why? Because you are having a large number of this one neutrons in a small volume. So the density will be very large. So previously we had the electron degeneracy pressure, but here the neutron degeneracy pressure will balance the gravitational collapse of neutron star, just like the electron degeneracy pressure, which prevents the further collapse of white dwarf. So we know neutrons are again fermions and they obey the Fermi-Dirac distribution and Pauli's exclusion principle. Thus, again we can say that your Fermi-Dirac statistics successfully explains the stable existence of neutron stars.